Hello everyone. Welcome to my channel, Machine Learning with Pats. In today's session, we'll delve into Lab Session 3, focusing on artificial intelligence and machine learning tailored for third-year mechanical engineering students at Pune University. In today's session, we're taking a hands-on approach to extract meaningful features from a given dataset. Exploring a case study on monitoring a triplex hydraulic pump, we'll craft a training dataset. Think of understanding your data like finding hidden gems. By the end, you'll master the process of creating a training dataset for machine learning classification tasks. Let's get started on this exciting journey. In this video, we set out with clear aims and objectives, introducing key terms and definitions essential for understanding the methodology. We dive into dataset exploration followed by a hands-on approach to feature extraction. Visualizing these features adds depth to our understanding, complemented by code walkthroughs and insightful inferences. Join me on this journey as we conclude with key takeaways, bringing clarity to feature extraction using Python. Before exploring the practical aspect of hands-on training for feature extraction, it's crucial to establish the aim and objectives. This provides a clear direction and purpose for our exploration, setting the stage for a focused and insightful learning experience. Let's define our aim. For today's lab, our aim to provide hands-on experience in applying feature extraction techniques on raw signals aimed at establishing training data for the condition monitoring of a triplex hydraulic pump. Let's construct objectives now. Our first objective is to identify the common failure modes and challenges associated with hydraulic pumps. Forward, we'll introduce a spectrum of feature extraction methods tailored specifically for hydraulic pump condition monitoring, providing you with a diverse toolkit. Next on our agenda is a hands-on demonstration of how to identify relevant features crucial for the health assessment of the pump. This step is vital in extracting meaningful insights from the data. We'll then delve into the significance of labeled training data in machine learning applications, emphasizing its role in enhancing the accuracy of our predictive models. Putting theory into practice, we'll actively engage in creating a dataset, labeling instances to represent different operating conditions and failures. This dataset will serve as the backbone for our machine learning endeavors. To enhance your understanding, we'll visually explore the relationships between individual features and the target variable by plotting them. Stay tuned as we navigate through these objectives, building a comprehensive understanding of feature extraction and its practical applications in hydraulic pump condition monitoring. Let's explore a few key terms and definitions crucial to our understanding of hydraulic pump condition monitoring. We'll delve into concepts like condition monitoring, direct method, indirect method, and common failure modes such as cavitation, worn seals, and misalignment. Following that, we'll break down feature extraction and explore statistical features from different domains. Additionally, we'll understand the significance of training data, including attributes, features, samples, instances, and labels. We will begin with our first key term, condition monitoring. This is a systematic process where we track the performance and health of a machine or system over time. It requires continuous or periodic assessments of various parameters to catch any deviations from normal operating conditions. Now, the real significance lies in its emphasis on predictive maintenance. Condition monitoring becomes a crucial tool in identifying potential issues before they become critical failures. By monitoring equipment health in real time, we can strategically plan maintenance activities, ultimately minimizing downtime and reducing overall maintenance costs. It's all about staying ahead of potential problems to ensure the smooth operation of our machinery. Broadly speaking, there are two types of condition monitoring. Let's understand first method, which is called as offline method. In simple terms, offline methods involve the continuous monitoring of equipment during its regular operation. These methods utilize real-time sensors and monitoring systems to get instantaneous data, allowing for early detection of anomalies. This early detection is crucial for timely intervention and maintenance, ensuring the smooth functioning of the equipment. Examples of offline methods include the continuous monitoring of parameters like vibration, temperature, and pressure. These parameters act as indicators, helping us identify changes that could point to potential issues in the equipment. The second type of condition monitoring is online methods or periodic inspections and testing. They involve assessing the condition of equipment through intermittent inspections or testing, typically conducted during scheduled maintenance shutdowns. Unlike continuous monitoring, these activities are not ongoing but are performed at predetermined intervals. This can include visual inspections, non-destructive testing, and diagnostic evaluations. Examples of online methods encompass conducting oil analysis, utilizing infrared thermography, performing visual inspections, and employing diagnostic tools during planned maintenance periods. These periodic interventions play a vital role in ensuring the health and reliability of the equipment over time. Now, we'll move towards understanding various failure modes of the pump, laying the groundwork for our upcoming classification model. Understanding these distinct failure scenarios is essential as we wish to create a robust and effective machine learning model for pump condition monitoring. First on the list is cavitation. This occurs when vapor or bubbles rapidly form and collapse in the hydraulic fluid due to low pressure zones. This phenomenon can erode pump components, reduce efficiency, and compromise the pump's ability to generate sufficient pressure. The shock waves from bubble collapse can inflict damage on impeller blades and other surfaces over time. Next up is worn seals. This occurs when the seals within the hydraulic pump deteriorate or sustain damage, allowing fluid to leak. As seals wear, the pump's ability to maintain pressure decreases, leading to inefficiencies. Additionally, fluid leakage can contaminate the hydraulic fluid and potentially damage other components. Understanding these failure modes provides crucial insights as we work towards developing a comprehensive classification model for pump condition monitoring. Now, let's discuss additional failure modes of the pump crucial for our classification model. Third on our list is misalignment, imbalance, or resonance. These issues arise when pump components aren't correctly aligned or balanced, causing vibrational problems. This can lead to excessive vibration, stress on components, accelerated wear, and potential structural damage. Timely identification of these issues through vibration monitoring is crucial for prompt resolution. Moving on to piston or plunger wear, this occurs due to continuous contact with hydraulic fluid and other components. Wear can result in loss of precision in pump operation, reduced volumetric efficiency, and increased fluid bypass, ultimately leading to decreased pump performance and potential damage to other parts. Our fourth point is damaged gaskets. Gaskets play a vital role in sealing different pump components to prevent fluid leaks. When damaged, gaskets can cause fluid leakage, leading to a drop in system pressure and contamination of hydraulic fluid, impacting overall pump performance. Understanding these failure modes equips us with the knowledge needed to develop a comprehensive classification model for effective pump condition monitoring. Now, let's explore the concept of feature extraction. This process involves transforming raw data into a set of relevant and distinctive characteristics. Its primary goal is to reduce the dimensionality of the dataset by creating a smaller set of more informative features. In the realm of condition monitoring, feature extraction becomes crucial as it entails selecting and transforming data obtained from sensors or measurements into meaningful statistical parameters. This step is vital for distilling essential information and preparing our data for effective analysis and model training. It is important to understand different domains in which the data can be represented. First is statistical features extracted from raw signals represented in the time domain. Time domain features offer insights into the behavior of the signal over time. This includes key statistical measures like mean, variance, skewness, kurtosis, and more, directly derived from the time series data. These features provide valuable information about the central tendency, variability, and shape of the signal. Understanding these statistical aspects enhances our ability to discern patterns and trends within the data for effective feature extraction and condition monitoring. Look at the picture below. It depicts a comparison of temperature trends over time, specifically focusing on the years 1995 to 2016. The blue line represents the temperature trend for the year 1995, while the red line illustrates the progression of temperature trends from 1996 to 2016. The observer notes that drawing meaningful conclusions directly from the visual representation is challenging, highlighting the importance of statistical analysis in such situations. The suggestion is to calculate the average temperature trend across all the years to gain a more comprehensive understanding. Statistical feature extraction is emphasized as a crucial step in machine learning to derive meaningful insights from data. In this context, it involves extracting relevant statistical measures, such as averages or other higher-dimensional statistical representations, to facilitate a more robust and accurate comparison between temperature trends over the years. In essence, the observer advocates for a systematic and statistical approach to analyze the temperature data, recognizing that visual representation alone may not provide a complete and accurate understanding of the underlying trends. By leveraging statistical feature extraction techniques, researchers and data analysts can uncover hidden patterns and variations, contributing to a more informed interpretation of the temperature trends captured in the graphical representation. Let's consider this case in detail. Imagine having a dataset with time series temperature readings from a hydraulic pump collected at regular intervals. The goal is to extract meaningful features to understand the pump's behavior and potential anomalies. In the raw data, we have temperature readings like 25 degrees Celsius, 26 degrees Celsius, 24 degrees Celsius, and so on. For feature extraction, we calculate the mean temperature over a certain period by considering summation divided by number of observations. The mean temperature provides an overview of the average operating temperature during that specific period. This extracted feature offers a concise summary of the pump's thermal behavior, providing valuable insights for condition monitoring and anomaly detection. As you deal with signal processing, understanding the frequency domain becomes crucial for extracting valuable information. The frequency domain provides a unique perspective on signals by revealing their underlying frequency components. One fundamental concept in frequency domain analysis is the dominant frequency. This represents the frequency component with the highest amplitude in the signal. Imagine the signal as a combination of different frequencies, and the dominant frequency is the one that stands out the most, playing a significant role in shaping the overall behavior of the signal. Next, we have spectral energy, a metric that quantifies the distribution of energy across different frequency components. Spectral energy provides insights into how the signal's power is distributed among various frequencies. This information is valuable for understanding the overall intensity and characteristics of the signal. Bandwidth is another crucial feature derived from the frequency domain. It refers to the range of frequencies over which the signal exhibits significant energy. A narrow bandwidth indicates a concentrated set of frequencies, while a broader bandwidth suggests a more spread-out distribution. Understanding the bandwidth helps in identifying the breadth of frequency components present in the signal. To access these frequency-specific details, one commonly employed technique is the Fourier transform. This mathematical tool allows us to transform a signal from its time domain representation to its frequency domain counterpart. Through this transformation, the hidden cyclic patterns within the signal become apparent, aiding in the identification of vibrations and other periodic behaviors. In this analysis, we'll explore the transformation of time domain temperature readings from a hydraulic pump into the frequency domain using the fast Fourier transform, FFT, and focus on the feature extraction, specifically the identification of the dominant frequency component. We begin with a dataset comprising time series temperature readings from a hydraulic pump, collected at regular intervals. The time domain representation of this data gives us insights into the temperature variations over time. To unveil the frequency-specific information within the temperature readings, we apply the fast Fourier transform, FFT. This mathematical technique allows us to convert the signal from the time domain to the frequency domain. Essentially, it decomposes the complex signal into its constituent frequency components. Upon transforming the data, we focus on feature extraction, specifically targeting the dominant frequency. The dominant frequency is identified as 0.1 Hz. This means that within the temperature readings, there is a prominent cyclic variation or regular disturbance occurring at a frequency of 0.1 cycles per second. So, the dominant frequency is 0.1 Hz. This dominant frequency of 0.1 Hz holds significant variations. This value indicates that there is a recurring pattern in the temperature readings, manifesting as cyclic variations or regular disturbances. In the context of a hydraulic pump, such cyclic variations could be indicative of specific operational behaviors, such as rotational cycles or periodic changes in load. Understanding this dominant frequency provides valuable insights into the inherent dynamics of the hydraulic system. In practical terms, this information could be instrumental for predictive maintenance or anomaly detection. Identifying and monitoring dominant frequencies allows engineers and analysts to recognize patterns or deviations from the expected cyclic behavior, enabling proactive measures to be taken before potential issues escalate. When exploring signal analysis, incorporating the time-frequency domain becomes essential for a more comprehensive understanding of variations in both time and frequency. This domain allows us to extract statistical features that capture the dynamic behavior of a system. Let's delve into the key concepts and techniques involved. In the time-frequency domain, we aim to capture how the frequency components of a signal evolve over time. This is crucial for understanding the dynamic nature of a system, as it provides insights into changes occurring at different points in time. The spectrogram is a powerful tool for visualizing the frequency content of a signal over time. It represents how the power or amplitude of different frequency components changes as the signal progresses. By using color to indicate the intensity of frequencies at various time points, the spectrogram offers a detailed representation of the signal's time-frequency characteristics. Wavelet analysis involves the use of wavelets, which are mathematical functions that can be applied to a signal to reveal localized information in both time and frequency domains. This technique is particularly useful for capturing transient events and abrupt changes in a signal, providing a high-resolution view of time-frequency variations. EFT is another technique employed to analyze how the frequency content of a signal changes over time. It involves dividing the signal into short segments and applying the Fourier transform to each segment. This approach allows for a time-dependent representation of the frequency spectrum, enabling the tracking of dynamic changes in signal. The time-frequency domain features extracted through these techniques are instrumental in understanding the dynamic behavior of a system. By tracking variations in frequency components over time, analysts gain insights into how different operational conditions or external factors influence the signal. For example, in the context of machinery, monitoring changes in the time-frequency domain may reveal fluctuations in vibration patterns, indicating potential issues or variations in the operating conditions. This information is crucial for predictive maintenance, anomaly detection, and overall system optimization. In the analysis of temperature data from a hydraulic pump, the objective is to move from the time domain to the time-frequency domain for a more nuanced understanding. We begin with a set of time series temperature readings, collected at consistent intervals, representing the pump's thermal behavior over time. To extract meaningful features, a wavelet transform is applied. This technique enables a detailed examination of how the frequency content of the temperature signal changes dynamically as time progresses. The focus here is on capturing not only the overall trends but also the finer, time-specific variations embedded within the data. The resulting is a spectrogram, a visual representation showcasing the variations in temperature frequencies throughout the monitoring period. This spectrogram acts as a comprehensive map, illustrating how different temperature components fluctuate across both time and frequency. Interpreting this spectrogram reveals valuable insights into the hydraulic system's behavior. The time-specific variations exposed by the spectrogram provide a detailed look at transient temperature changes. In other words, it unveils moments of temperature fluctuations that may be temporary or occur at specific points in time. So, what is training data? It refers to a labeled dataset used to train a supervised classification model. This dataset includes input features paired with corresponding output labels, where the labels indicate the correct classification or category for each input. The primary purpose of training data is to instruct the machine learning model on recognizing patterns and relationships between input features and output labels. By exposing the model to a diverse set of labeled examples, it learns to generalize and make accurate predictions on new, unseen data. The training process involves presenting the machine with labeled data, allowing the devised learning algorithm to analyze and learn from it. The goal is for the model to generalize its understanding, making accurate predictions when presented with new, unlabeled data. Therefore, in supervised learning, the term training data aptly reflects its role, as the labeled examples supervise and guide the model throughout the learning process. Now, let's break down the components of training data. It comprises two key elements. First is input feature. They are the measurable characteristics or attributes of the data instances that the model utilizes to make predictions. In a practical example, like a classification task in images of fruits, input features could include pixel values, color histograms, or any other relevant features describing the visual attributes of the fruits. Second is output label. They are the predefined categories or classes that the model aims to predict based on the input features. Continuing with the fruit classification example, output labels might represent categories such as apple, banana, or orange. Each data instance within the training set is paired with a specific output label, indicating the correct classification or category. By having a clear understanding of both input features and output labels, we equip the machine model to learn and generalize patterns effectively, facilitating accurate predictions for new, unseen data instances. Look the picture below. In supervised learning, the model is trained on labeled data, where input-output pairs are provided. The algorithm learns to map inputs to corresponding outputs, predictions on new, unseen data. On the other hand, in unsupervised learning, there are no labeled outputs during training. The algorithm explores patterns and structures within the input data without explicit guidance, often involving tasks like clustering or dimensionality reduction. Alright, now we will summarize all key terms. Let's start with attributes. Think of them as the unique characteristics or properties of our data. In our case, it's the temperature at a specific point in time. Each temperature reading, like 25 degrees Celsius or 26 degrees Celsius, is an attribute. Now, let's talk about features. These are born from attributes through something we call feature extraction. Picture this: we calculate the mean temperature over a certain time period, say, the average being 25 degrees Celsius. That average is now a feature crucial for machine learning models to grasp and learn patterns in the data. Moving on to samples or instances. These are the individual data points or observations within our dataset. So, each temperature reading we have, whether it's 25 degrees Celsius, 26 degrees Celsius, or 24 Celsius, represents a sample. Together, all these samples form the dataset that our machine learning model will use for training and analysis. Now, labels or classes. In the supervised machine learning game, labels are like the final destination. They're what our model is trying to predict. Say we're working on pump fault diagnosis. The labels here could indicate the health status of the pump during a specific time period. If everything is working fine, the label might be normal. But if there's a hiccup, it could be faulty. Labels give our model a goal to strive for in its prediction. Let's continue building our framework. Start by gathering a diverse dataset that includes both healthy and faulty signals from your system. This dataset is the raw material for your machine learning model. Once you have your raw data, it's time to extract meaningful features. This involves calculating statistical measures like mean, mode, and standard deviation. These features will help your model identify patterns and characteristics in the data. With your extracted features, you now create the training dataset. This involves pairing the extracted features with their corresponding labels indicating whether the signal is healthy. This labeled dataset serves as the basis for training your machine learning model.
Now let's explore some dataset. Here we will consider this example by MATLAB, which shows how to use a Simulink model to generate fault and healthy data. The data is used to develop a multi-class classifier to detect different combinations of faults. The example uses a triplex reciprocating pump model and its leak, blocking, and bearing faults. The CSV file titled raw simulated data.csv has this raw dataset. In the second picture, you can visualize the time intervals in the first column and corresponding pressure values for different conditions of a triplex hydraulic pump in further column. Each row represents a specific time point, and the columns represent different scenarios or states of the pump such as healthy and various faulty conditions. Here's a general description of the CSV file. First column has time values at which the pressure readings were recorded. First column has readings for the healthy condition of the pump. Column No. 2 to 8 have pressure readings for 6 different faulty conditions of the pump, that is from faulty 1 to faulty 6 in a sequence. Let's understand the data characteristics. The values in each column are numerical, representing pressure readings. Dataset appears to have a time series structure, with pressure values recorded at regular time intervals. The pressure readings vary over time, and different fault scenarios exhibit distinct patterns. Healthy readings are presented as a baseline for comparison with faulty condition. The plots which are visualized after running the code can be seen here. The first plot shows how a pressure varies with respect to time when the pump was healthy and there was no any fault. Second plot similarly shows the variation of pressure over a time when pump was suffering from faulty type 1. However, variation between these two conditions cannot be examined just plotting the raw data in time domain as shown in these pictures, and thus we need some assistance. Similar to previous slide, the plots shows the variation of pressure over a time when pump was suffering from faulty type 2 and 3 in picture 1 and 2 respectively. The abnormal variation for fault type 2 can be visually perceived, however same is not true for fault type 3. Now when we visualize plots for fault type 4 and 5, a trend is clear. The fault type 4 shows declining trend and type 5 shows an increasing trend. Same is also true for fault type 6, as it shows a very abrupt changes perceived from sudden increase and decrease in the trend. However, comparing all the cases and making decision based on visualization is not possible. Thus we need some techniques to quantify the difference between various classes.
In today's lab we will explore features listed below. So we have mean, mode, median, standard deviation, variance, skewness, kurtosis, maximum value, minimum value and range. Our goal here is to extract key features from pressure readings of a pump under different conditions. We've got 7 labels representing pump states: healthy, faulty 1 through faulty 6. Let's understand flow of a code. Our data has time values in the first column and pressure readings for each condition in the subsequent columns. Each condition has 5,712 values, and will process them in pockets of 100 consecutive data points. To optimize our analysis, we'll divide the data into 57 pockets, each containing 100 consecutive readings. This sequential approach enables us to calculate features per pocket, ensuring a systematic exploration of the entire dataset. Processing in pockets has its perks. It allows us to perform a more granular analysis, capturing trends or changes in patterns within smaller segments. This can be crucial for understanding localized variations in the data. Now, here's the interesting part. Features will be extracted incrementally as we process each pocket. This means we get insights into the evolving nature of the data, adapting our feature selection along the way. By processing the data in smaller pockets, we enhance our adaptability to the evolving data. It's like zooming in on specific sections, potentially capturing variations or patterns that might be missed in a broader analysis. First, we will extract features for healthy pump condition, column 2. As explained earlier, column 2 has 5,712 values. We will process 5,712 values by dividing them into 57 pockets, each containing 100 consecutive data points. This approach enables us to calculate features for each 100 values sequentially, optimizing the analysis of the entire dataset. To do this in a Python code, just specify the hashtag set the window size, 100 data points, window_size equals 100. When you run the code, statistical features for 57 samples of healthy pump condition and label each sample as healthy in either first or last column. Then repeat this procedure for other columns for remaining faulty conditions of pump. So now, we will extract features for faulty 1 pump condition, column 3. We will process 5,712 values by dividing them into 57 pockets, each containing 100 consecutive data points. When executing the code, the statistical features will be computed for 57 samples corresponding to the healthy pump condition first. Subsequently, the analysis will continue with the calculation of statistical features for 57 samples related to the faulty 1 pump condition, appearing just below the healthy pump condition result. Then repeat this procedure for other columns for remaining faulty conditions of pump. So, at the end you will get 57 samples for each pump conditions such as healthy, faulty 1, faulty 2, faulty 3, faulty 4, faulty 5, faulty 6 one after the other. You will get total samples equal to 57 times 7 is equal to 399. This is your training data. Let's understand a step-by-step exploration of the entire code, examine it line by line to gain a comprehensive understanding of each component. First few lines are usual. Import pandas as PD and import numpy as NP. Import the pandas library as PD, and the numberpy library as NP. Pandas is used for data manipulation and analysis, while numberpy is used for numerical operations. Next line df equals PD read_CSV, raw simulated data.csv, reads a CSV file named raw simulated data.csv into a pandas data frame called df. Moving ahead. In order to extract the time column, use time_column equals df, time. To identify columns with numerical data, excluding the time column, you can use numeric_columns equals df.select_types, include equals np.number.columns.tolist. In order to set the window size that is 100 data points you can use window_size equals 100. This window size will be used for calculating statistical features over subsets of the data. A function called calculate_statistical_features takes a column as input and calculates various statistical features within a window of the specified size is shown here. The for loop function iterates through the data in windows of the specified size, window_size. For each window, it calculates various statistical features using numberpy and pandas functions and appends the results to the corresponding lists. Here, the name of the column is extracted dynamically using column.name and added to the sample_names list. And finally, the function returns a pandas data frame containing the calculated statistical features for each window. The data frame has columns for the sample name and various statistical features. Result_df equals PD data frame, columns, initializes an empty data frame called result_df with columns for the statistical features that will be calculated. Now to calculate statistical features for each numeric column, for if loop iterates through each numeric column, excluding the time column calculates statistical features using the calculate_statistical_features function, and appends the results to the result_df data frame. Lastly, save the final data frame result_df to a new CSV file named statisticalfeatures_combined_all_columns.sv without including the index column in the output CSV. However, you can choose the name as per your requirement. The full code is listed here for your ready reference. The full code is listed here for your ready reference. The full code is listed here for your ready reference. As we conclude today's session, I want to encourage you to keep exploring, keep learning, and most importantly, keep being awesome. The journey of knowledge is a shared one, and I can't wait to see where it takes us next. So, until next time, thank you once again for being a part of the Machine Learning with Pats family. Your curiosity and enthusiasm inspire us to keep pushing the boundaries of what we can achieve together.